Hello everyone, this is Asrag and let's get started with our JAX ML scaling book, chapter 2 on TPUs. TPUs was invented by Google, and these are domain specific architectures that are specialized to do matrix multiplications and vector multiplications manipulations, which are the fundamental units of modern deep learning. So if we get started with a basic architecture of TPU, you can see here you have a high bandwidth memory, which is used to store the weights activations. You have a scalar unit, you have a vector processing unit, which is going to do element wise operations, and a matrix multiplier unit. So TPU is specifically designed for matrix multiplications and vector multiplications, and that's what they are going to do this very fast. Now let's look at each of the components of TPUs. First is matrix multiplier unit. In matrix multiplier unit, you have each MXU is able to do this operation of taking a 8,128 matrix and another 128,128 matrix and doing this operation, and this is done every 8 cycles with a systolic array. And in later generations like TPU v6e, this 128 has been increased to 256. So if your matrices are not in multiple of 128, so when you shard a matrix and let's say the last shard has a dimension of 64 instead of 128, so we need to pad them to 128 so that you can use MXUs directly. And most of the tensor cores in TPU have 2 to 4 MXU, and TPU v5e is a inference specific architecture from Google. So you can see one of the TPU component MXU, each HBM is connected. We're talking about v5e architecture, which is inference specific architecture, which is connected to 4 MXUs here in one tensor core. The next component is in TPU is vector processing unit, VPUs, and these are responsible for operations like ReLU activations or pointwise addition or multiplication between vectors. So if you have a vector, then you can you don't need a MXU. You can go to a VPU, and in VPU you have two axes. One is the sublane axis, and another lane axis which is 128 wide, which is which the number that we saw with MXU, and each subcell in this has 4 independent arithmetic logic units to do these operations. So VPU can do operations of, like, you have in a VPU you have 8,128 cells, and each of them has 4 ALUs. So total of total ALUs per core in your tensor core is around 4096, and VPUs generally have a clock cycle of 1.75 gigahertz, which comes down to around this many flops. So if I go back to how to think about TPUs and go to the spec sheet here, if you see TPU v5e, the flops per chip in BF16 is around 2e to the power 14. These are the number of flops per chip, and these are the MXU units. And if you see VPUs, the flops is 7e12. So flops from the MXU units in TPU is much higher than compared to VPU. So yeah, matrix multiplication have higher number of, those are like charged with more number of floating point operations as compared to operations like ReLU or pointwise addition and multiplications. The next one is vector memory, and it's a on-chip scratchpad located in the tensor core close to the compute units. So all the activations and weights in HBM needs to be transferred to vector memory in it, which has bandwidth of in a TPU V5E architecture. It has around this much bandwidth, and this data is now transferred to MXU or VPU to do the operations. Again, VPU is for vectors like ReLU, uh, pointwise addition, multiplication, and MXU is for matrix multiplication. And this bandwidth is 22 times faster than this bandwidth. So, but this size is much smaller. Like the vector memory is around 128 megabytes, and HBM is 16 gigabytes. So there is like a trade-off between the bandwidth and the size of the memory. Then the next another subcomponent in TPU is vector registers, and vector registers are basically the compute units. They are the closest to the compute units. So from vector memory you go to vector registers, and um, the compute units like MXU and the VPUs do operations on these vector registers. So these are like around kilobytes, and these are like blazing fast to get to, like the register memory is like blazing fast to get to the compute units. So if you see the difference between TPU and a GPU, so you have HBM, which have all the data, then it transfers to vector memory, and then it goes to vector registers, and then it goes to MXU or the VPU, and then it goes back to vector registers, VMEM, and then return back to HBM to persist. However, in GPUs, it's also near similar. Like you have the host memory, and the host memory is responsible to launch a kernel on GPU, and in GPU you have HBMs. Similar here, you have HBM, and this HBM have goes to SRAM, and then it goes to the CUDA cores to do the operations. GPUs also have L1, L2 cache to and the register memory to have more hierarchy in memory, and you can like clearly see like GPU and C has like more general purpose as compared to TPU, and TPUs are only made for matrix multiplication and vector operations. Um, Next is in a TPU you also have a host similar to GPU, and the host is connected to all the chips to launch a kernel on the chips, and each chip that we saw earlier has high bandwidth memory, and they are connected to MXU units and also VPUs and vector memory, and before going into a MXU or a VPU it has to go through the vector register. Now coming to the bandwidth in a TPU is you have different compute units connected, and your host is from where you're launching the kernels, and this host can be connected by this DCN network, and across TPU units you are connected by ICI, and HBM is for each compute, each tensor core. Uh, a tensor core generally has 2 to 4 um, sorry yes. So this was the diagram, and each TPU is basically a chip here, and this chip can have one here in TPU V5E architecture. Each chip or TPU has one tensor core, but they can definitely have more than one tensor core. They can jump from range 2 to 4 tensor cores, and so all so this is the bandwidth of in a TPU V5E architecture, and this is followed in rest of the architectures too. Um, if you look at the bandwidth, so HBM has more bandwidth as compared to ICI, which is inter chips connect, and DCN is host to host, which is the slowest. So we need to try to avoid DCN communication and prefer HBM, which is at the um, chip level, and ICI is also to transfer directly from two nodes here. Now another interesting thing with TPUs is you can request for slices. So let's say you have a TPU pod. This is your TPU pod, which is of the size 4, 4, and now you can request different shapes to do computation. So here, notice the red one. Here you are requesting 2, 2 here. So this is going to be very relevant when we'll discuss about different kind of parallelism. So suppose you are doing data parallelism, so you can access 2, 2 here, 2, 2 here, at the back, here, here, and here. So you can shard this entire pod into 4 data parallel size, which will process in data independently. You can break down your data into 4 subset, and each of these slides will process different data points. And you can also, inside a data parallel size like this red one, you can break it down into two subsets, and you can now break matrices and do tensor parallel. In tensor parallel, you break down matrices and to reduce the number of activations. Don't worry about this, we are going to discuss this in the future lectures, or please check out my LM lectures distributed lecture series. But yeah, in tensor parallel we break down the matrices, so each data parallel can break down into 2 tensor parallel units. So this is how you can request different TPU slices. Now let's start with solving some questions. So the first question that I'm going to go is this one. Say you want to sample from a 200 billion parameter model in a BF16 that is split across 32 TPU V4P architecture. How long it will take you to load all the parameters from HBM into the systolic array? So sorry. So you have a 200 billion parameter model with BF16, which is 2 bytes. 1 byte is 8 bits, just 2. So BF16 is 2 bytes. You have 200 billion parameter into 2, which translates into 400 gigabytes of. It's like your total memory from the weights of the model is around 400 gigabytes. So you have 32 TPU V4P architecture. So if I go back to here, V4P is here, and it has a HBM bandwidth of 1.2 in E12. So I have copied over this 1.2 10 to the power 12. So you have 32 TPUs and you have 400 gigabytes. So each TPU needs to load 400 gigabytes divided by 32, which comes around 1.25 10 to the power 10 data to be read per TPU, which is around 0.12 gigabytes. Around 12 gigabytes per data point. Now the time taken is how much we are going to read per TPU divided by the bandwidth, HBM bandwidth, and this comes around 10 milliseconds. Now let's move to question 2. Question 2 is, consider a TPU V5E pod. How many total CPU hosts are there? How many TPU tensor cores? And what is the flops for the whole pod, and what is the total HBM? So if I go to TPU V5A architecture, it has a pod size of 16 comma 16. So the total number is 256 TPUs, and host size of 4 comma 2. So hosts basically manage those TPUs. And so this is host, you can like think of like the CPU in CPU for a TPU. And you have 4 comma 2. So the first question is, how many total CPU hosts are there? So to see the host size, you have a pod size of 16 comma 16, and your host size is 4 comma 2. So the total number of CPU hosts is we take the total number of pods, and each host is responsible to manage 4 comma 2. So you have 32 CPU hosts. Let me just enlarge this a little bit. And the total number of TPU tensor cores is 256. So your pod size was 16 comma 16, which is around 256 TPUs. And if I search here inference if optimized, so older TPU, if you see here, older TPUs have separate memory and regarded as two separate accelerators. Inference optimized chip like TPU V5 only have one TPU per core chip, one tensor processing unit per chip. So we have 256 is the pod size, and each one has one tensor core, so we have 256 tensor core. Now if we go back here, so if you see flops per second per chip for TPU is 2e to the power 14. So we have 256, total flops would be 256, and this is per chip or per tensor core, so we just need to multiply this for total flops. And then if we go back again, it has HBM capacity of 16 gigabytes, and you have 256 total pod size, 256 into 16, which comes around 4 terabytes of total HBM memory. Now if we go over the same exercise on TPU V5P, which is here, and it has a pod size of this 16 to 20 into 28, and each CPU host is managing 2 comma 2 comma 1. So the total number of CPU host is going to be the ratio 16 20 28 divided by 2 into 21, and this comes around 2240. And so the second question was, what is the number of TPU tensor cores? And for number of TPU tensor cores, I would have to check here. So V5P configurable. It was written as mega core, yeah. So this is like TPU V4, V5, V6 TPUs, known as mega core, and which has shared memory and can be thought as large, twice the flops. This is true for so so these generally have 4 around, yes. So one mistake that I did here is if you we're discussing about TPU V5P architecture, we calculate the host number of hosts, and in the flops, so if you go through the mega core, and they generally have 2 tensor cores per chip. So so we need to multiply it, like this is our total pod size. And if I go here, we were discussing about TPU V5 architecture, and we were looking at the flops, which is 4.6 into 10 to the power 14. So we have that value here, and this is the pod size, and each chip has two tensor cores in this architecture. This is one of the mega cores that we consider. So it has two, so we need to multiply it by 2. Similarly, for total memory, we have the pod size, and each one has a tensor core, and each tensor core has um, each one has two tensor cores, hence we multiply by 2. And if I go back again here, this has a HBM bandwidth of 96 gigabytes. So this was uh, just analyzing the TPU v5e and TPU v5p architecture. Let's go to the next question, which is question number 3. Sorry, I'll close this answer. So imagine we are forced to store a big weight matrix A of type bfib16 d, f and a batch of activations b, d in a host DRAM, and want to do a matrix multiplication on them. This is running on a single host, and we are using a single TPU v6G chip. You can assume B is less than D and F is equal to 4D. So we will go back to our visualization here. So we will select first TPU v6E architecture, and this fills in the peak compute and the memory bandwidth. But if you notice here, the question is assume PCIe bandwidth. So the data is on host DRAM, and with PCI bandwidth we are going to transfer the data to the compute units. So the memory bandwidth that I have here is for chip to chip, and if I converted it into PCI bandwidth, now see this. So for TPU v6E architecture, now this is the reach point, which comes from the total number of flops that we can do. Okay, let me also check if I'm doing BF16, F is 16. So this is your reach point with 55,000, and this is your arithmetic intensity. See, no matter what is your batch size, you can have 200k batch size, can have 50k batch size. No matter how much batch size you have, you are never going to hit this. You are never going to go into compute bound region, and the reason for that is you are transferring your data through PCIe. Now let's look at another type of visualization to make this more clear. So suppose I have the same visualization. Like we have B here, D, F, and you have different TPU chips, and you have precisions, and let's skip BF16 for now. And here, this one is more important. You have PCIe, you have ICI, which is chip to chip, and you have an ICI bidirectional, which is chip to chip, and which is a little bit more faster. Like because it's bidirectional, you can transfer data. Like it's kind of a ring attention or ring topology where you can transfer and receive data at the same time. So if I convert this into host into chip, see the difference between time. So this red line is communication time with increasing batch size, and this blue line is computation time with increasing batch size. See, there is a wide gap between it. So now, no matter how much batch size you have, these are never going to come close. Like at batch size of, if you can see here, 127k, sorry, it's like around 120k, you have some closeness to between communication and computation, but there is a big gap between these two lines. Now if I go to bidirectional, So you can see that the gap narrows. So at batch size of 38,000, which is achievable, uh, you can have your communication and computation going close by. So you're not bottlenecked by one of them. So um, so if you have host to chip, then you are always spending a lot of time in communication. This is what we are also seeing here. If when I decrease the memory bandwidth because of PCIe, our compute intensity can never reach the compute bound region. Um, and the next, yeah, we went over this question. So as for this question, you cannot reach to compute bound no matter how high the batch size is. And now let's discuss this question. Let's say you want to multiply a weight matrix, an activation matrix, and B is of unknown batch size, TPU v5 architecture. How long will this matrix multiply as function of B? So we are going to select TPU v5 architecture. Let's keep it down actually. And yes, you have this compute bound, and you can see the range value is 241. Let's see what's the data type. It's int 8. So it's int 8. So your range is going to increase now. Um, so you can increase your batch size, and like it will keep on approaching the compute bound region, and the B star, or which is the idle batch size after which it will start to be compute bound, is around 260. Also one thing, so the computations that JAX ML in this book they are doing is when you have B is much less than D and F. So they have this assumption, hence some of the answers are going to be a bit different if you assume that, which is fine. Like, but we were in close approximation because we don't have that assumption, and we can increase the value, and you can see this B star, which is where you start, after that you start being compute bound, is closer to what the JAX ML book has. And now if you see this, what if you run this operation out of vmem, and how long it will take as a function? So we as we discussed here, if you go back to our slides here, so HBM to VMem is around this, and this is for TPU v5 architecture, and this one is around 22 times faster. So if you look at our arithmetic intensity, so your bandwidth by the accelerator, this bandwidth is going to be 22 times of this, which is, let's say, around 160. So you can see, like, your batch size now, your idle batch size goes down by a lot, like after which you start to hit in the compute bound region. So if your bandwidth has increased a lot when you have transferred the data to vmem, and there you can, your memory bandwidth is like 22 times of the HBM bandwidth, so you need a smaller batch to reach into compute bound region, the happy place, like because if you go to the compute bound, you can take the advantage of increasing flops by NVIDIA or from TPUs. So your batch size comes down to around 12 optimal batch size. We went through this question, and now let's discuss this question. Let's say we have TPU v5 architecture, which is 4,4. Let's say we want to send an array from TPU 0 to TPU 3,3, and let's say per hop latency is this much. How soon will the first byte arrive at its destination? To understand this question, let's so um, so this is the TPU v5e architecture. You can see here we have compute units here, and only in TPU v5a you have one chip, and one chip has one tensor core. So you have this setup, and if I go back to this question, I drew a smaller, just a minimal version of that setup, and I have this line which represents this host. So you can see like two sets here, 2,4 here, 2,4 here, and they are joined by the host. So I have this question, and now you have BF16 of this matrix, so which comes around 1.7 E7, 10 to the power 7 total, total like data you have, total bytes of data you have. And if I go back to our spec sheet, TPU v5e architecture, and we need the ICI bandwidth link, which comes around 455 E10. Because why do you need the ICI? Because as we saw here, these are connected by ICI. So you have ICI bandwidth, and so it is like bidirectional, like this compute unit can receive and also send the data. So it is bidirectional, so it you have 9e10 total bandwidth you can have. So you need to transfer this much data. So the question is how you need to transfer data from here till here. So if you see there, how many hops are there? 1, 2, 3, 4, 5, 6 hops. And you can send some of the data this side and send some of the data this side, and you can get the data. So you can like cut your data into two parts and send in this stream and in this stream. So you have like two directions. Uh, so if you want to send this much data and you have that much bandwidth, so you take around 12088 microsecond. And in the question there was that to send there is a latency of 1 microsecond. So for 6 hops you have 6 microseconds, so total will be 194 microseconds. For the last question, I need to go through sorry, I open answer. Like I need to go through the chapter 3, and we will come back to this question because this requires some knowledge about all gather and or gather, and how much memory, how much bandwidth is considered in gather and all gather. So this is it for this lecture, and hope you see on the hope I find you on the next one. Thank you.